All right, here we go, round two, properties complex conjugates. Well, I hope you're feeling very confident with if a z is equal to a plus bi, then a z star, or the complex conjugate, is equal to a minus bi. And at this stage, you should readily be able to tell me when you multiply complex conjugates, you always get a squared plus b squared. Okay, yeah, that's got to be automatic. Got to be automatic. So z equals 3 minus 2i, z star is equal to 9 plus 4, or equal to 13. Do I have to write the complex conjugate? No. I'm just looking at the a and the b, squaring them both and adding them. All right. So properties of this is something that if we're together, this would be up there and I'd say go, and I'd give you 15 minutes in class. What we have is we have one complex number and another complex number. So this is the idea of, it's kind of the inductive thought where you do a few examples, a few experiments, and then you're kind of like, wait a minute, I see a pattern. So if you wouldn't mind, I would love for you to use those two complex numbers, and as fast as you possibly can, write these down. I would write them in order like they are in those columns, and I've circled some things that maybe you want to look at and see if there's any kind of relationships. All right, I'll let you pause and come back to that. Oh, if you want, you can do with another round of complex numbers. Maybe you'll see the patterns a little bit better. All right, well, let's see how you did. So at this stage, maybe you can have you can conjecture. If you take, and what the first one is saying here is, if you take a complex number, do the complex conjugate, and then do the complex conjugate on that one, I would hope that maybe you have the ability to say, wait a minute, you're just kind of undoing it. There you go. The second one, maybe you saw that if you add the two numbers and then take the complex conjugate, it's equal to another process, and that I'll just give you is, wow, isn't that cool? You can take the complex conjugates first and then add them, and you'll still get the same thing. All right, let's try and fill in the other ones or take a shot at it, and we'll see how we do. All right. Okay. Hopefully you got something like this. Very cool. We did this one together, this one together. When you subtract them, exact same thing. So some people say, hey, you can distribute the complex conjugate. It's not a weird, it's a weird way to say that. You're not distributing it. So we'd say the conjugate of the sums is the sums of the conjugates. I'll say that again. The conjugate of the sums is equal to the sums of the conjugates. Sounds fancy, because it is. All right. So sort of the same idea here, same idea here. Oh, this is nice. This is really nice. You could take a complex number to a power, multiply over and over and over again, and then take the complex conjugate, or you could take the complex conjugate first and then take it to the power. All right. IB loves this idea of taking numbers and saying, hey, what would happen that would for sure get a real number or a purely imaginary number? When we say are real, that means the imaginary part is 0. So, and then I just threw that in again. I know I started with it. It's the most important thing about complex conjugates that you're going to run into as far as algebraic manipulation. So it needs to be in your back pocket. All right, so like I said, this class will be about a little bit more about proving. So how would you show that this works? Well, showing is just kind of working out both sides and seeing if they're equal. So I decided to do the one on the right. Well, you have nothing to work with. You have to have the ability to change what Z1 and Z2 are. Do not use specific examples. That only proves it works for those particular complex numbers. So you want to introduce A plus BI and C plus DI. Does it have to be A, B, C, and D? No, mix it up. Throw an M in there, throw an N, heck, F, G, whatever. All you're doing is plugging it in, doing the operation, and seeing if the left side equals the right side. So if you're slow and deliberate, everything's going to work out. A times C, B times BI times DI is BDI squared, and I squared is -1. That's where this is coming from. Hey, I might be going too fast for you. Go ahead and work this out. Show everything, combine like terms, you'll get it. I did the same thing here and worked it out. I had a little problem with the negative sign, so I had a plus here and a minus here, but I had two negatives, so I factored that out front, and sure enough, those are equal. Okay, so we've proven that the conjugate of the products is equal to the product of the conjugates. Ah! All right, I'll leave that one up to you. Pretty much all of these are done the same way, and I'll bet you're going to be asked to do all of them. All right, I don't understand this, so I worked it out, and I just wanted to show you that what is capital X and capital Y? That means just put all the real part together and all the imaginary part together. I actually took this one off your homework. So to get you started, we're just trying to show that this equals this. You better, they do a nice thing and tell you, hey, start with this. So I did the first side, z squared, get something, and then find the complex conjugate of that. I think we've talked about this. A plus BI quantity squared is equal to that. Get used to it. It's going to happen a lot. That's my X and that's my Y. Notice I kept my I right here, just kind of separate. Well, the complex conjugate of that is going to be the minus, of course, and I'm not too sure how throwing it into capital X, capital Y helps you, but to understand that to group those into the real and imaginary, I think is important. All right. So this is definitely, if you want a 7 on the exam, you walk into here and you're like, okay, I can work with this. First of all, the Z, and maybe you want to keep the Z in there, maybe you don't. There's not a lot you can do with that right there. So we're going to plug in the A plus BI, and we're going to manipulate this so we have a real part and an imaginary part. What they're asking for here and here is, can we look at this number and pick values for A and B so that if we have purely imaginary, we're saying that the real part is equal to 0. Can we pick A's and B's so the real part drops out and we have something times I? Over here, it would be like, can we pick our A's and B's so that the imaginary part goes to 0 and we have something by itself on the real part? So real part, imaginary part. First step is kind of fun. So you plug in your A plus BI, you group your real part and your imaginary part, and the whole point of learning 4C is, hey, I can divide complex numbers, even if they look really complex, like the complexity of the complex number. But it's just a complex number. As soon as you get that, you got a real part and imaginary part. Complex conjugate, the real part, and then you just change the sign. You do a little multiplication. No, this is not the end of the world. This is totally doable. I kind of look at this as one thing and one thing, one thing and one thing, and I like to write it out. So the A minus 1, A plus 1, A minus 1, BI, BI, A plus 1, and BI times BI. And that's the top. I'm not too sure how they did it. Yep, they did the same thing. Remember, this is A minus 1 times A plus 1, and that gives you the A squared minus 1. And there's that. Ooh, they wrote that out. That's nice for you. yeah, I have to write a plus 1 squared plus b squared. They threw in that I squared just to make sure that you see that. And you get some good stuff here. The bottom is an entire real number, so you have done all the work. And so if you split the real part and the imaginary part, everything without an I on this side, everything with an I on this side, and there you go. So to remind you of the problem, the purely imaginary is what we're after, or the purely real. So let's say we just say, hey, what about A and B to make this purely imaginary? Well, that means we want this quantity to be equal to 0. So when is a squared minus b squared minus 1 is equal to 0? So whenever a squared minus b squared is equal to, yeah, okay, 1, then that side is going to be equal to 0. Therefore, it's purely imaginary. However, dang, are there any situations where this is satisfied and 2ab is equal to 0? Well, there is. You got to kind of, if you're going to take this to that level 7, you can't really say that A, you have to say A can't be 0 and B can't be 0. Why? Because 2ab cannot equal 0. If it's equal to 0, there's no imaginary part either. So we got to keep that alive. Have we thought about everything? The last thing I would think about here is, can we divide by 0? Or is that just going to put the brakes on this whole problem and nobody's going to have any fun? So really kind of consider the situation where we're dividing by 0. And that's only going to happen when A is equal to -1 and B is equal to 0. So this situation can't happen. Can't happen. Hey, I don't know if this is what you're going to see in the highest level textbooks in the world, but I'm just trying to make the point of what to think about. 1, great job. You made the real part equal to 0. Hey, great job. You kept the imaginary part alive, and then you kept Chuck Norris away. Chuck Norris is the only one who can divide by 0, so you said, hey, we don't need you. We'll just not get in that situation. All right, another 12-minuter. Thank you. Have an amazing time with this.